Yes, sir. Thank you.
Okay. So as I was trying to say, so when you're trying to build something which is fairly complex, when I say fairly complex, how do you define something is fairly complex? So when you're trying to build, let's say, a simple paper airplane, you just need a piece of paper, and you could just be a single person, could fold it using your hands, and you could roughly fold, have the crease on the paper, doesn't need to be very precise and accurate. And as long as the paper airplane meets some basic requirements of being aerodynamic, you can throw it and it will start flying, right? Now, obviously, that's an airplane. Maybe it can carry a few ants and probably some insects, but but there is probably no real uh, there are no real challenges or specs being enforced on it that it should carry people of so many people, has to carry so much load, should always be reliable, should be extremely safe, never fail more than, let's say, 0.1% of the times, or the components on that should not. So when you start putting in all these complex specs, what's going to happen is that the system starts becoming complex, because now each and every piece there has to meet certain requirements, because we know that the probability of the whole system to work reliably depends on the probability of the individual pieces to work reliably. Uh, may not be uh, may not be the same value, but the system obviously has to be more reliable than the components which are there, right? So when you start putting all these requirements and constraints, it's not a simple system anymore. It's not. So if you're building when let's say Airbus is building an aircraft, or Boeing is building an aircraft, or let's say HAL is building Tejas. So the challenges and the constraints are significant. It's not just same as a building a paper airplane, right? Now, have you have to procure components. The components should meet the specs. The even the simplest of screws should meet certain stress and loading requirements. Obviously, engines, turbines, or and all these other aspects need to meet certain other requirements. So it's basically not a trivial thing. And VLSI, not recently, but since its earliest days, we're talking about the earliest systems or chips having nearly 50,000 transistors, and then having 4 to 5 different complex elements. So right from its earliest days, people realized that if you have to start adding more and more complexity, you have to partition this. You have to start hiding the internal details and complexity, because it is very interesting to know all the complexity. For example, we know that at the end of the day, everything is physics, right? For example, all transistors are based on certain quantum dynamic effects, quantum mechanical effects, right? The whole MOSFET and the bipolar junction transistor works on quantum principles. But does it mean that for someone who's trying to build a circuit or a system needs to know quantum physics and needs to be able to solve Schrodinger's equations and so on? I mean, it'll be great to know that, but it's of no value to build a reliable transistor, right? And so, which means that you have to hide the complexity. You should be able to abstract. Hiding the complexity and having an approximate or a fairly reliable definition or a function of it is abstraction, right? And abstraction is required for any complex system. It's not just electronic system, but electronic systems are some of the most complex, and I would say that probably the most complex systems that actually exist. But any complex system requires abstraction for it to be able to for you to be able to take it from just very simple elements to a full system which is able to do some complex functionality. So in the case of an electronic computing system, the field has been abstracted into various stages or elements here. So you can think of it like stages, you can think of it like pieces or elements, and you can think of it like uh, domains or expertise. And you are free to look at it in any different way. And that's exactly what abstraction does. Because of abstraction, the beauty of abstraction is the interpretation is open. and that also allows a lot of innovations to happen, right? So now you can think of it this way, that there is device, there's quantum mechanical aspects, quantum physics aspects, and you have to build, you have to understand how electrons flow and how the holes flow through the semiconductor substrate, and which means you need to know the physics aspect, and that's required to be able to write equations which could then explain some complex phenomena, which is how transistors work. So you would need some device physics experts, and people who know some device physics and some material aspects would probably be used, could work together to build transistors, right? Or you require material and chemical sort of understanding of how materials behave and how they are actually fabricated or processed, and how some aspect of it interacts with physics to build a transistor. And so there is this part abstraction called devices, which is primarily taking care of transistors. And in our case, could be transistors, could be even wires, all the non-active elements, um, capacitors, inductors, and so on. And then once you start putting together devices in some interesting, simple to complex ways, you can start building circuits, right? So obviously, real circuits are all analog. So the lower in the abstraction is analog circuits, are analog circuits, and then um analog circuits are what people always look at any transistor level phenomena, right? But digital circuits are basically a step above analog, in the sense they completely abstract the way the signal flows and the signal levels, and therefore you don't really need to worry about all possible values of the signals, and you just care about just high, low, true, false kind of thing, and it's just a binary. So all digital circuits that we currently use are all based on binary schemes, which means you can abstract this whole complexity into digital circuits, and then using digital circuits, you can because it's binary scheme allows us to build logic, because logic is nothing but true false statements. So you can build more complex elements using this. And then when you have logic, what is just a logic any use of? You can build it to build some sort of a complex microarchitecture, where based on certain conditions and operations which you can define, you can build some complex arrangement of flow of data and information. And then you can sort of build upon this to offer architecture, and then goes into software side of things, operating system and application softwares. Right. So that's the level of abstraction that has been added in this whole domain. And so which means if you're looking at it as a timeline, it can be like, for example, a foundry comes up with some interesting physics, builds some new kind of transistors, and then new kind of transistors results in some interesting analog circuits, which possibly also results in some interesting digital circuits, or both, because maybe the interesting transistor allows us to have low power, or at the same performance, or so for the same performance have much lower power, or the performance is better at low voltages, and so on. And then could make it, we can probably build more functionality in the smaller area, so more logic can be packed, more density, more interesting architectures. For example, uh, uh, an interesting new CPU architecture or a new accelerator, right? And so on. So similarly, you can also think of it like domains of expertise. There are people working in this here, in another domains here, here, and so on, right? So in this talk, and in this set of series of talks, we're going to touch upon some of it here, not much, but primarily going to focus on some of it here, but a lot of it is going to be in these areas: digital circuits, logic, some microarchitecture, and some architecture aspects. And we'll sort of not go into details of all of it, but we will sort of keep going back and forth to keep it interesting, and also to motivate the audience to understand that the whole field is very interesting, and there's a lot of value in doing some research or exploration in this field. Okay, so when I talk about this whole concept of abstraction, right? So abstraction is important, and abstraction results in something which has been called as the 3 whys of the design process, which I think is a very interesting nomenclature, which David Harris talks about in his book. and I think people have talked about in some of the literature, is are the concepts of hierarchy, modularity, and regularity. So what are these three Ys? The Ys are coming from here: hierarchy, modularity, and regularity. So hierarchy involves, if you have a large system, you're trying to break it down into partitioning it into smaller pieces and elements, which can then be independently be pieced together like a jigsaw, and the whole thing then comes together and allows us to and work in this divide and conquer type of approach, right? So hierarchy is extremely important, because without hierarchy, it's like saying that you're trying to build the whole Boeing aircraft in one single piece. Unless you are able to break it down into smaller pieces, which could then be able to build on them independently, the whole thing is too big and complex, requires too many people and too many experts, and there's no way that you can actually build it reliably, right? This picture is again a form of a hierarchy, sort of partitioned it into pieces here. Modularity is when you have each of these pieces having clear defined functions and expectations or interfaces. Interfaces means what's input and what's output, and they have clear defined functions, which means what they're supposed to do and what they are doing. And when it's clearly defined, which means we clearly know when it is not doing its job, and we have unanticipated side effects like errors or bugs or whatever. So because if we know about it, and how we are sort of clearly defined its operations and what are its expectations, which are interfaces, I think it becomes very easy for anyone to be able to use some of those pieces and make them work. And the regularity, again, is a very important thing, because hierarchy and modularity are great to have, but unless each piece which you have broken into the hierarchies, and which each piece which is modular, if you cannot ensure that the piece coming from different people or from the same person at different points in time, right? If it is not regular, or basically very similar to what you have aligned on, then you have a problem, because without uniformity and regularity, you have to then treat each of these pieces as different entities, which means there's a lot more work. Think of it like the construction industry. Without bricks, there is no way you can be able to build a good structure, because each brick on its own is very regular, which means any architect or any mestri or any sort of construction person could just talk in terms of number of bricks required in the room or number of tiles required in the room, and so on, right? So the whole structure allows you to talk in terms of a very abstract or a simple quantity, which is just the element which you're talking about. And as long as it is very regular, which means it's meeting its specs, and one element to the next element is roughly similar. Obviously, in a real world, you cannot make it to be precise, because that exists only in theory. But as long as it's meeting the requirement within some tolerance, plus minus something, and that's good enough for all of us. And that's what I think these modules, which are regular, mean. So hierarchy, modularity, and regularity are extremely important concepts. And I think that's heavily used in the VLSI design industry and the design flows. So any questions here? Okay, so let's quickly talk about some of the ways we partition or try to have a nomenclature for the different kinds of electronic design systems. So this nomenclature is actually is more historic, and it's not applicable, I would say, anymore, because a lot of these things have gone to a state where you can't just say something is just an FPGA or an ASIC or and so on, because each of these chips have become so complex that they have taken in features from the others, and it's become a more complex setup. And in fact, what's happening is we are reaching a point where you clearly cannot define and use this nomenclature to say, okay, that chip is FPGA or this kind of chip and this chip is an ASIC or not an ASIC and so on, right? But let's sort of just go with this historical nomenclature. So application specific integrated circuits, ASIC. These are, I think, as the name implies, or it's sort of used to imply, these are special purpose and have very limited scope and application. They are like very focused functionalities. For example, people trying to build some video or audio accelerators, which means chips which are meant to do a lot of this video processing or audio processing at a much higher throughput and performance requirements. Then deep learning accelerators, you may have heard about it. Someone was asking about whether VLSI industry has any influence of ML. ML, any form of ML which you are right now experiencing, for example, your Hello Google or Alexa, as you call it out, is actually happening at the back end, either on your phone or on the cloud. So, and without VLSI, it's just not possible to get good response times and good performance there. So Google has invested a lot of its resources to build dedicated accelerators for deep learning acceleration, and this sort of it is a form of an ASIC. I'm going to probably briefly touch upon this near the end of today's talk. Then application-specific standard products, examples could be USB interfaces, DDR chips, and so on. These are, again, similar to application-specific, but they have very sort of general-purpose usage. System on chip is basically, or SoC, is when you have a lot of, not just one, but multiple complex processor cores or compute cores sitting on the same chip. Microprocessors, microcontrollers, digital signal processors, on-chip memories like caches, then hardware accelerators, a lot of peripheral functions like DDR controllers, USB controllers, PCI controllers, and so on. So pretty much all the chips these days, which are used heavily by us, for example, all the laptop chips, like Intel and AMD laptop or server chips, Qualcomm Snapdragon sitting on the Android phones, a lot of Android phones, Apple's SoCs, right? Are basically Apple's chips are basically SoCs. They have multiple microprocessor cores. They also have some microcontrollers for a lot of firmware type of temperature, voltage type of tracking. They have some digital signal processing chips for audio and video related applications. And then they have hardware accelerators for AI ML. And then they have to interface with the DDR memories, and they have to allow USB slots to be plugged in, PCI to be plugged in. So they have controllers there. So these are complex SoCs. And the most interesting thing is that SoCs these days are built using the same techniques as what ASICs are used. So in a sense, SoC, you can think of it like a superset of ASIC, which means all the applications or IPs which you or cores which you build for an ASIC, if that all comes together in one single chip with a lot of different ASICs, it's effectively an SoC. So as I was saying, there's no clear nomenclature anymore. So I think most of the complex chips these days, people just call them as SoCs. No one says ASICs and so on. But in general, if you talk to people in the industry, when they talk about ASICs, they mean either SoC or they could mean ASIC. And also it could also mean the design flows which are being used. ASICs, ASSPs, SoCs use similar design flows, which I'll touch upon. And that's all based on a cell-based design flow, standard cell-based design flow. And then other than this, we have other interesting class of chips called the field programmable gate arrays or FPGAs. The FPGA is basically a software programmable silicon chip, and it is reconfigurable, that is reprogrammable, and it has significantly shorter design cycle, and it gets used for prototyping, emulation, and in the recent days, it's also being used for building application-specific accelerators. So again, as I was saying, ASICs and FPGAs, the difference between them has come down significantly, because people are actually even using FPGAs for building accelerators and not just building ASICs there. So the examples are AMD's Xilinx FPGAs, and then Intel's Ultra families like Cyclone, and there are companies like Lattice, Acronix, and so on. I'll skip this slide. I touched upon this, and then okay. So let's quickly talk about what are the traditional or historical comparison points between ASICs and FPGAs. So the column here, the white, represents the metrics or the comparison points. The red column obviously is for FPGAs, and the yellow brown one is for the ASIC. So time to market. So time to market basically means how quickly can you get your product out for the sort of application that you're trying to build, or the industry that you're trying to target, right? So FPGAs are extremely fast, and extremely fast for the obvious reason that FPGAs are not meant, historically, were never meant for building a specific application. They were reconfigurable, which means software could program them. So which means companies like Xilinx or Altera had to just build a sea of configurable logic, and they had to send it to the foundry, fabricate it, and while it's getting fabricated or the development is happening, they could get the software working, and by the time the chip comes back from the foundry, they can test it by running the software, and the software could program any kind of functionality. You could build a CPU, you could build a controller, you could build an accelerator, whatever you want. So which means for a customer, this whole lead time of development of the FPGA is not visible, and he only has to actually take the FPGA from the distributor or from the company which is selling it, and which means he can buy it from the shelf, and he could have an architecture, he could put it in the RTL, and he could run it on the FPGA software, implement it, which means the whole design development time could be as small as 2-3 weeks for testing, prototyping. Whereas an ASIC is significantly large, and it could be depending on what sort of complex IPs and SoCs. So it's a complex SoC you have how many complex cores or functionalities you have, or whether you have a new architecture. This could be as large as 3 years to be as small as like a year. So we're talking about a significant difference in the time to market between these two. NRE, which is the non-recurring engineering costs. Non-recurring engineering costs. So FPGAs is low. So when we say this cost is primarily for the people who are trying to build the application to the market, or the product to the market, and for them, which means, let's say if it's an end user like me, I have no development cost for the FPGA. I only have to buy an FPGA. So which means I don't have to invest in engineers or CAD tools or software or any other overhead to build the FPGA, because it's handled by Xilinx or Intel or Ultra and so on, right? Whereas for ASIC, and if I'm trying to build a product, I have to invest in a lot. So therefore, there's a big difference in this NRE cost. The design flows is simple, again, because the FPGA company provides me the software, and I have to primarily know just RTL design. Historically, RTL was good enough. These days, people can even just know software like C++ or C, and they can program an FPGA. Whereas in the case of an ASIC, the design flows are extremely complex and require a very specialized knowledge and so on. And in each of this comes from separate vendors, which means the whole process is pretty expensive. The unit cost is FPGA is high, and that's basically that's basically for the obvious reasons that none of these costs are handled by you, right? Or the developer or the person trying to bring the product to the market, and it's all handled by the company, which means the unit cost is going to be slightly higher or significantly higher than what an ASIC costs. So ASIC, let's say if you have a market of, let's say 10 million chips, and so once you are able to get 10 million chips to the market, even as you are able to get a very small volume, because you invested so much, after you get a high volume, the cost per unit is going to be very small. Whereas an FPGA, that is high. So historically, there was always a trade-off point for which where beyond a certain volume, ASICs were more interesting and cheaper when the volume was high, and FPGAs were used to be used only when the volume was small. And this is again a historical fact, but not very valid in the current scheme of things in the latest technology nodes. Performance, FPGAs, because they are software programmable, they are extremely slow. And ASICs can be extremely fast. Power consumption, because it's software programmable and it is reconfigurable, power consumption is going to be high, because to make something reconfigurable, you have to add more logic, more transistors, because you need to be able to make it function for different functionalities. So which means there's an extra overhead to add more transistors, more control, more muxes in the logic. So therefore, for building a simple function, again, you have to use a lot of transistors. So that's why it's high. ASICs are extremely efficient because you have to only build the function that you care about. And the unit size, because ASICs are custom designed and custom built, which means the specs can be very tight. So you can have a very small unit area. And FPGAs, because of the configuration reasons, can be fairly big for the same functionality that you're trying to build. And this is sort of an interesting plot. I think can try to look at it when the slides are shared, but this shows how for the number of units, which is x-axis is the number of units, y-axis is the cost per unit, the total cost, not what per units, total cost scales with the number of units for an FPGA versus an ASIC. So the bold line is for an ASIC, and the dotted line is for an FPGA. And as you notice, when the volume starts becoming more and more on the x-axis, the cost of an ASIC, actually the dotted line is actually FPGA. Dotted line is dotted line is actually. Let's talk about this line here. The first point here. The red one is actually ASIC, and the red one is ASIC, not dotted line. The red line is ASIC, and the black one is actually an FPGA, and the dotted line are basically the technology nodes, and the bold lines are the new technology nodes. So if you notice here, generation N means an older node, and generation N+1 means a newer technology nodes. Now, what you will see is if you take the technology node generation N, which means an older node, and so what you will see here is that the dotted line, the black, which is basically for the old node, the FPGA, which is black, right, beyond certain units starts becoming more expensive. And ASICs, they start with a high cost, and because their slope is small, why? Because the unit cost is less, but they have a big overhead, which is the NRE, the development cost, which is one-time cost, is fairly high, but the unit cost is small, which means as you keep adding more and more units, the cost is increasing slowly, and which means once you cross a certain volume or the number of units, it becomes cheaper for an ASIC than for a FPGA, the black one. And what's happening is that is still the case in the latest technology nodes, where the black one is crossing the red line. But what you will notice is that compared to older technology nodes, you actually need to have a much higher volume for ASICs to actually become more economical than FPGAs, which means the value of high volume development of ASICs is actually coming down because this whole NRE and the total cost of ASIC is significantly going up. This is sort of an interesting data point, because historically, when people have talked about FPGA, they used to draw these curves and say, okay, this volume, which means I can go for an ASIC. And what this does is, and it's sort of a very good paper to read, how it shows that the trends are still there, but you need to go for extremely high volumes for ASIC to be competitive in terms of cost than an FPGA. And in the recent technology nodes, people have actually stuck with FPGAs, and because of the benefits that it gives, because of complex architectures like deep learning and machine learning, which are evolving so rapidly that investing in one ASIC, which caters to only one standard of the algorithm, is not going to be useful and not make you competitive. Let's say if you have invested so much money, you would like the product to be active for a few years, but because the standards are so frequently changing, it makes sense to stick with an FPGA where you can continuously reprogram and reconfigure and keep evolving rather than investing in an ASIC. Unless you have huge volumes like companies like Qualcomm, Intel, AMD, and so on, where it clearly makes sense. And they also are extremely targeting extremely high performance. FPGAs will not give high performance, but if your primary comparison point is cost and unit cost, then I think the trade-offs are becoming more interesting, and FPGAs are extremely competitive these days. Okay, any questions here? All right. So this is how a quick view of how the FPGA design flows look like. This specific plot, this specific image shows the various aspects of the not FPGA ASIC flows, and the dollar tag signs here show the sort of the cost involved in each of these steps, or what's the investment required in some of these steps, and uh, what's interesting is these costs are becoming more and more um, with advancing technology nodes. So you must be hearing about 14 nanometers, 10 nanometers, 7 nanometers. People are talking about 5 and 3 as well. So a lot of these costs are significantly going up, and I think the in this specific image, uh, there's a distinction between extremely expensive and some sort of a bare minimum price here. So if you notice, there's a red tag and the orange one. So let's talk about some of these. So there are EDA design tools. These are CAD tools, as I said, extremely important for the VLSI design flows. And ASIC design flows have a lot more CAD tools, and that's expensive. One of the expenses involved. This comes from companies like Synopsys, Cadence. Hard IP cores. These are specific, unique functions or IPs which you are building in silicon for your reuse across the same technology node and across products. Like for example, AMD or Intel build their CPU cores, or the GPU cores, or some machine learning accelerators. That could be some of these cores, and it's fairly expensive because you have to support design teams. You have to actually pay the cost of fabricating some of these, right? Or and get some foundry support. The actual foundry support comes here. The tape out. Tape out means releasing the mask to the foundry, and the back-end silicon work. That's also a fairly intensive work. A lot of engineers required for reliable production and for meeting execution cycles. And then silicon shuttle, or MPW, which means the wafer on which the chips are being produced. They are basically have to be paid for, and then fabrication, test and development, because once the chips are fabricated, they are diced, and they are tested, and they have to meet some specific specs at some early stage. If they are not, they are thrown away, or if they are not yielding well, which means number of parts are not meeting specs, the foundry and or the test development team gives feedback to the architecture and the design teams. That means they may have to come back and check at these phases and see if there was an issue which they missed, or some new observations from the silicon. This they have to incorporate. The whole cycle sometimes repeats, and it's pretty expensive. And then after the chip has been tested, bare chip has been tested, which is just silicon substrate, uh, then you integrate this in a package, which is now ready to be put on a motherboard. And then and this whole process could sometimes repeat. Now, it's fairly expensive process, because with new features being added every day, the cost of development, especially on this end, the back end and the foundry, these three aspects are extremely expensive here. Okay, I'm going to jump into the ASIC design flow. Any questions here before I branch to the next few slides? Okay. So what we're going to do is we're going to cover the next few slides, talk about some of the high-level aspects of the ASIC design flows, and some of it will be touched upon when we talk about uh, specific things like synthesis. We'll touch upon that briefly, what aspects of it, maybe some clocking aspects, some design and circuit design aspects, and optimization aspects, which are probably relevant here, will be touched upon when I'm going to in the coming days when I'm going to talk about that. But as the flow as an overall may look like this. This is just a representative view of it. There could be a lot of additional details which are not described here, but it's just to, as I said, abstract the whole flow, right? So at the start of the flow, you have a specification. There will be an architecture team which based on marketing or uh, product marketing or product engineering and customer interaction teams could come back and interact with the silicon architects, and they would say that okay, customers are looking for these features, these improvements, or the competition is coming up with this, or the customer is looking for specific improvements in let's say power or performance is for the same power is bad, and all these sort of things could be coming in as specification. So the architect could go back to the drawing board and he would say, okay, let's review what uh, was done earlier in some of these areas. Okay, not looking good, let's improve this. Some of the solutions may already exist within the company. Sometimes the solutions may not exist, which means they may have to research the literature or hire people from outside, and or maybe completely spend some time and come up with a completely new specification or an architecture aspect which could be a completely revolutionary thing, which may have to be done because the existing methodology or approach is just not yielding the requirements, right? So that's all done at this phase, specification and architecture phase. And once an architecture is fairly stable or frozen, um, and the actual implementation of the architecture into the flow friendly uh, uh, or design friendly aspect is done what's called as an RTL design, where I think you may have heard of Verilog and VHDL as some of these languages which are used to code the architectural spec. Now, this RTL design is basically nothing but taking the high level aspects and converting this into primitives or design friendly aspects from an high level architectural aspect. So architecture is basically just a set of functionalities which needs to be met, right? And the way things have to flow, the data flows or control flows, or they interact, and what should be the frequency, what should be throughput, very high level aspects. But when something has to be actually be implemented, you need to be able to take all of the high level aspect and start getting into the detail. In a sense, now you're going down the details of the flow, where the architecture is now broken down into pieces which are now extremely design friendly. For example, there's this design methodology called synchronous design methodology, which is what typically people use when they use RTL. uh, and synchronous design means it's basically all designs operate on sequential elements which are clocked by a signal called which are controlled by a signal called a clock, right? So synchronous design methodologies are used, and then people build a lot of these architectural features into this using the synchronous design methodologies into actual design elements, and which are called modules, which are using languages like VHDL, Verilog, and there are new languages which have come up these days, but VHDL, Verilog are still the dominant ones. And for a lot of AI ML applications, a lot of these companies are providing hooks for even software programmers to be able to implement an architecture into a design And these days there's an approach called HLS, where you have a hook to write a C++ or a C code that goes through a software which is called an HLS synthesis software, which converts that high-level spec into an RTL. So in any case, the flow would require an RTL implementation of the architecture spec. So once you have an RTL, you obviously have to verify it. So there is this here, RTL verification, RTL design or architecture, and they have to keep sort of iterating here if there are issues in the RTL which doesn't meet the architectural spec. So keep evolving, and once it becomes stable or nearly stable, you go on to the actual more detailed aspects of the flow. You implement what is still a programming or a software construct into a physical element, which is in the case of ASIC flow, which are nothing but gates, right? Logic gates. And the logic gates are then sort of, they have to be designed with certain specs like power, performance, and area. So synthesis tools provided by companies like Cadence or Synopsys are used. For example, you may have heard about Design Compiler, RTL compiler, Genus compiler, and so on from these companies. That's used that reads an RTL, synthesizes the design, and then generates something called as a netlist. And netlist is very close to a physical structure. Now you have actual nodes or elements which are present in the design, which you can actually structurally try to analyze. There is usually no structure in an RTL design because RTL design is very behavioral, or it describes a behavior. But once you reach synthesis, you clearly have a structure in the design. You could identify, okay, there are NAND gates, there are NOR gates, there are inverters. As some of you may know already, these are the logic elements or logic gates that are used to implement logic functionalities. So the RTL synthesis takes an RTL, takes in something called as a library or a standard cell library, and then builds a netlist. The netlist then flows through the other aspect of flow. DFT is designed for test, which means whether the netlist can yield properly when you go to silicon, and if it cannot, where are the potential faults which may happen. So they may add some additional logic to be able to test for those faults, because no one wants to ship a product to a customer which may have bugs or faults. So we would like to catch that at our end when we test it, as we saw here in the testing and development flow. So which means we need to provide hooks in the existing netlist. So DFT, which means it's going to add some extra area and power cost over what the architect thought about, because this is unavoidable, because of the obvious fact that the whole fabrication process is can have some faults. So we have to invest in some area for this. And once this is there, then we actually go to the next level of the actual lower level detail, which is the floor plan. The floor plan is nothing but the actual, just like a floor plan of a house or a complex. You really are trying to put together the pieces which are taking up certain area on the chip cross section, chip on the silicon substrate, and then how you want to utilize the width and the height, or the length and the breadth of the chip, how you want to place specific blocks, where to place them, how to connect them, how to distribute signals between them. All that is at a high level planned in the floor plan stage. And then placement, where you may, once you have done that, then you take this netlist from which is available at this stage, and then you use the software tools to guide the placement of the individual cells, the logic cells, so that you can meet certain specs. And then CTS is called clock tree synthesis. This is again a very unique requirement for synchronous designs, because synchronous designs work on a global clock, which means a single clock controls a lot of logic. The whole design may not just have one clock, but one clock could control a lot of aspects of a logic. So that signal, which is critical, called the clock, has to be distributed and needs to meet its spec for high performance or low power. So that is taken care in clock tree synthesis. And then once this is completed, so far all the signals that we've talked about are only virtual connections based on some net names, but the nets have to be converted into actual wires, and that is done by this step called routing. So routing is actual physical connections of wires flowing from, let's say, one gate to the output to the another gate's input, and so on. So this whole connectivity or connections from end to end is done in this routing step. Once routing is completed, you have to take it through a flow, a step called a sign off. Sign off means whether the whole the chip, which is nearly complete at this point, is meeting its spec in terms of performance, power, and timing. Why timing? Because these are electrical signals which we are sending from one point to the another, and they have some performance requirements, which mean they need to be early or slow, and they have some power requirements, and so on. So whether all the specs are being met or not. So once this is done, and sign off also involves a lot of physical checks. For example, whether the power is hooked up properly, whether the fabrication requirements, like certain devices or certain physical aspects like wires are not very close to each other because they could short or they could cut open, and so on, are avoided. So all these aspects are covered in sign off, and not just the electrical checks. Then it is sent to the foundry. It's the process is called tape out. It's sent to the foundry for fabrication. The foundry then fabricates it. It usually takes, depending on what priority the foundry assigns to the company which is shipping its um, the tape out database. For example, TSMC prioritizes Apple as one of its major customers, and Apple gets the highest priority by TSMC. So let's say if it's the tape out database is coming from Apple, then it probably gets the highest priority. That the chip may come back in 3 months. Whereas if it's a small company, low priority, could be taking as much as 6 months to 8 months. And once fabrication is done, then there's actually an intermediate testing step which is not shown here, but testing happens at multiple phases. Post fabrication, there's a testing happens. This is called wafer level testing. And then once wafer level testing is complete and it meets the spec, then the chips are taken from the wafer and they are diced, which means they're cut and they're packaged. And then once it's packaged, because it's now ready to be plugged on a motherboard, before that, there's another level of testing which happens because the interfacing or the integration of the chip on the package has not changed anything or not degraded something. So it's tested, and there are specialized equipments called testers which are used. Could be running a packaged part, and then once it's ready, you have a chip which I think once it meets all the specs is ready to be shipped to the customer in high volume or whatever the volume that the company is looking to target. Okay, I think we'll quickly skip these slides, but any questions before I talk about some of the specific backend? I talked about this, but any questions here? Okay, I think the slides here also talk about a lot of these specifics which I touched upon here, high level, in these slides. Front-end design, I talked about some of these, the architectural aspects, and then what the RTL aspects are covered here. Please go through this, and maybe I think if you have any questions over the coming days, you can bring it up and we can discuss. And as I was saying, the backend design. So I think another way to sort of describe the flow is front end versus back end. This is, I think, this is a very common terminology people use. Let's talk about this. So front end is, I think, primarily the pre-physical stage of the chip design flow, or specifically the ASIC design flow. So that involves specification, architecture, the RTL aspects, the verification aspect, and people sometimes bring in synthesis to this side, but I think, yeah, in general, synthesis stays on the front end side because you still it takes an RTL as an input, and then the DFT, which sometimes can come this side or this side. So this is the front end side of the flow, and the back end where you have clearly the netlist as input, and you have actual physical elements and pieces put together of the flow planning, which means actual chip area or the bounding boxes and the whole connectivity and flow of signals, power, all those things are planned and analyzed here. Comes in here, placement, CTS, clock tree, as I said, and then the rest of the steps makes up the back end here. So as you go further down the flow, you are getting closer and closer to the actual physical chip. And so the back end are the steps which are closest and the most relevant to the physical chip. And the front end are the steps which are early in the phase and extremely close to the architectural aspects of the chip. So this is a snapshot of an extremely old Intel CPU, the 8086, one of the precursors to the early x86 architecture. This came out in some I think late 70s. So you can see that even though this is probably not a big CPU, there's a lot of complexity even in this one, and even this kind of not very complex chip required all the requirements, as I discussed earlier, the abstraction, the hierarchy, the three whys, which need to be handled so that this kind of complex system could be built. And as we start adding more and more complexity, as you would see in some of the recent chips, uh, these levels of and these aspects are becoming more and more important, and the abstraction, the three whys, and not just that. Now, in addition to that, you also have various aspects of the design flows now becoming extremely high level. For example, software guys who want to write some very efficient machine learning or deep learning hardware solutions, they don't want to learn the RTL, like the digital Verilog, because it's more physical, closer to the physical electronic circuits, and they may not have exposure or background in it, but they obviously understand algorithms. So they want solutions where they can directly write an algorithm or a C++ code, which is in high-level software, and be able to implement, build a netlist, and then take it to chip design flows, either in an ASIC or an FPGA, and that kind of support is also now coming in and becoming very prevalent. It's called the HLS-based approach. So there is more and more push to have higher and higher level of abstraction, so that the complexities are better managed, and even people with less and less specialized experience and expertise are able to exploit the benefits the technology is providing. So these are, I think this is how routing, a simple view of how routing would look like. So these are wires, and these are representing wires flowing from this point to this. And in the case of routing in ASICs, or in general in VLSI, we have something called as metal layers. So because you can't just route on one plane, because if you're trying to cross or reach 2 points, connect 2 points, and if the path in between is already taken up by another wire, the only way you can now go is through orthogonal route. You go up and then take a parallel plane and then come down. So the routing technology, in a lot of technology notes, you may hear about metal layers or metallization. So the recent technology nodes, you would have metal layers going up to as high as M16 or M17, which means there are 16 metal layers or 16 layers on top of each other to connect different points of the chip to each other. So in this example here, so what you notice is that you have this red metal and the green metal. These connections between them, these are called vias. That's basically a small hole drilled in the metal, and then some metal connection to allow interconnection between these two. and then signal flows through this, and then flows this side or that side, and then could be either dropping down, going to the transistor, and then so on, right? So it's fairly complex. In the early technology nodes, people could just do with 2, 3, or 4 layers of metals. In the recent technology nodes, with all the integration and the complexity of number of devices sitting in the unit area, people require 15 to 16 to 17 metals sometimes, metal layers on top of each other. So this is a simple view from how the floor plan tool and how the post-routed database may look like. There are some cores like this. This is some SerDes core, could be for a USB or some other DDR5 or something like that. And then there's another some IP or core here. There's some connection between these two, some routing going through, and so on. This is just an example of how the physical design tool and the routing and the placement tool may actually show how the blocks are placed, how they may be routed, how the routed database may look like. So I talked about sign-off. That's summarized here, some of the steps here. So let's quickly, since we're running out of time, let's quickly talk about the FPGA architecture. So one big difference, any questions before I move on to FPGA? Because that's another set of things. I have a few comments in the chat. Okay, any questions? Okay, so let's quickly move on to the FPGA architecture. So one of the, as I was describing earlier, one big difference between an ASIC and an FPGA is an ASIC is, builds upon a clean, bare silicon substrate, and right from the architecture to the other states of the design flow, the designers are responsible for putting in blocks or transistors or other sort of complex structures built using transistors, piece by piece, group by group, module by module, and try to use the whole silicon area which they are looking to use up, right? So they are sort of building things from scratch. Obviously, some of the blocks could be reused, but effectively what they're doing is they start from a bare substrate and they are deciding how to do things, how to place things, how to connect things, and so on. And that's very interesting and very useful, as I described earlier, if you're looking for extremely high performance or you want to build it for extremely small power, or you want to optimize it for very large, extremely large volumes, makes sense. But someone who wants flexibility or whose volume requirements are not so high, or in the current recent technology nodes cannot afford to pay the extra significant cost of full-fledged ASIC developments in the latest technology nodes, FPGA is the approach. And FPGA is built on a very simple concept where they have something called as a configurable logic block. And these configurable logic blocks are basically pre-built logic elements which can implement any kind of universal logic. We know that there are specific logic functions which are universal, right? Can anyone name them? Can anyone name some universal logic functions?
And or.
And
Nor.
Okay.
And
Okay.
nor.
And is not universal.
NAND
So
and NOR.
universal logic, NAND and NOR are universal.
NAND and NOR.
That's right. So NAND and NOR are universal.
Yes.
Why? Because if something is inverting like a NAND and NOR, it can also be built to build a non-inverting logic, which means, so NAND, NOR, and any logic which is built upon using them, like a multiplexer. Again, multiplexer is nothing but a NAND followed by an OR, or a NAND followed by a NOR, right? So multiplexer and some complex or a decoder, any complex arrangement of these schemes can allow you to build any universal logic. Now, what FPGA companies do is they have an optimized implementation of this universal logic, which they call as a lookup table. A lookup table is nothing but a mix of a decoding and a multiplexing set of elements with some set of registers provided, depending on how the company like Xilinx or Intel would anticipate the use, and they would provide these blocks which are now can implement any logic for a given set of inputs. So these blocks could be having, let's say, 4 inputs or 6 inputs and so on, which means you can effectively build any complex functions based on those inputs. And they would also provide some registers inside, so they can also build some sequential logic inside. Now this is repeated and uniformly repeated. And so this is like an extremely old FPGA. So it's not exactly in this form in the recent technology, in the recent versions of FPGAs, but this sort of addresses or covers pretty much the needs of any average hobby or an enthusiast person. Because unless you are looking to build some extremely complex system, you don't read the other complex aspects which are usually provided by FPGA companies. So this is good enough for us to discuss about FPGAs. So the CLBs, which are primarily logic blocks or universal logic blocks with a set of inputs and some registers, can cater to a lot of functionality and a lot of sequential state machines and sequential operations which could be completed in this specific block. They are repeated, and how they connected? They have something called as a switch matrix or interconnection blocks, interconnection logic, and this interconnection is completely software programmable. This is software programmable, and you have the CLBs, which again are configurable, which could be used to make any kind of logic or functionalities that you want. And this is how the thing would look like. So an example here, the internals of the of a CLB is shown here. So as I said, there's something called as a lookup table. Lookup table is basically
Arun sir,
an arrangement.
can I disturb you?
Sure.
I have one query, sir. Hello.
Yeah, please go ahead. Yeah, please go ahead.
Yeah, sir, because this Xilinx is a open source. I think all the faculty members, they have this open source tool. What type of projects we can carry for our students using this Xilinx?
Yeah, I'm going to come to that, sir. I have one slide which shows various different projects that you can do or systems that you can build using Xilinx FPGAs. I'll quickly come to that in one of the coming slides.
Okay, sir. Okay, sir. Thank you.
Okay, so these are some of the, as I said, some older FPGA architectures, but the more recent ones, as I said earlier, when I was comparing ASIC versus FPGAs, FPGAs are, in the recent technology nodes are full-blown SoCs. They are not just programmable fabric. So which means not just the programmable logic or fabric, which is a blue one here, you also have AI accelerators which is useful for deep learning. Then you have DSP engines. Then you have ARM cores, which are for application development. And then you have a lot of other complex controllers for DDR connections, for high bandwidth memory, and RF, and so on. So like a lot of integration is done in an FPGA SoC in the most recent ones. That an FPGA is just not a plain simple FPGA as shown here, but a more complex SoC. And that's basically because you can't build everything within the fabric, and it's also obviously more efficient to provide some custom or dedicated hardware here, and you still have the flexibility of using this adaptable or programmable logic which you can implement, and you can interface any new kind of logic here. So this is a snapshot of Xilinx's latest Versal architecture of FPGAs. Now, an FPGA design flow, as I compared the ASIC design flow, is actually fairly simple even though there are steps involved, but a lot of the overhead of understanding the silicon aspects is completely taken away by the company, because Xilinx or Intel Ultra are responsible for the silicon side of things. So the FPGA SoC, like for example Vertex from Xilinx, is taped out, and they are responsible for its production in volume, whatever they want. And once they get that, they integrate that in a board, which then gets used by, for example, Mr. Facker, Mr. HOD was talking about, as you're asking, sir. So there is this development kit which will be there for the FPGA, which comes as part of the FPGA board. And this development kit is something which is now on which a lot of the enthusiasts or students, or even prototyping and low volume developers could actually go and implement their product on this. The cost of software is completely free, as sir was saying, because of the fact that this FPGA software is automatically available once you buy this board. So for example, Xilinx provides the Vivado software once you buy their board. And on this, you can code through RTL, like VHDL Verilog as well. And in the latest versions of their FPGA boards, you can even use high-level synthesis, which means you can use C++ and then try to code that, write a netlist out of that. So if you compare versus an ASIC, the cost is fairly low, and you can clearly see here that the cost to an actual end developer is primarily this one, the board development here. The board, the cost of the board, and whatever is the development that he has to do on the board. For example, the actual architectural aspects, hiring the design team, or whatever, right? All that cost sort of comes in here. So compared to an ASIC, where you saw here, there's a fairly smaller overhead compared to an FPGA. And ASICs, as you saw in some of the early slides, are becoming less and less lucrative unless you have very, very aggressive and specialized requirement. People are sticking with FPGAs. For example, a lot of these 5G, the network development and the infrastructure which is being built is people are building with FPGAs, and they just keep buying new and new FPGAs, set up the whole infrastructure based on that, and they don't try to build ASICs anymore because it's too expensive for them. I'll skip this slide. I talked about this, some of the high-level frameworks which the recent FPGAs provide. You can read through this. And yeah, sir, so to answer or provide specifics to the point you were raising, so the potential applications on FPGAs are shown here. Yeah, please let me know. I think if you have any questions on this. So a lot of a broad range of applications. I was talking about 5G
Hello?
and 6. Yeah, hi. Go ahead.
Hello? Yeah, sir. This is Chandrasekhar from Mysore, sir.
Yeah.
Is I'm audible?
Yes, I can hear you.
Yeah, sir. Actually, the FPGA board, what you have said, can I implement on this board the Python program, whichever I have been going to execute?
You
That
want to
means
implement what?
I will convert. I will convert my FPGA, that is Python code into a Verilog. That's sure.
Yeah, I think if there is a software support for it, it should be possible.
Okay.
I think you can read this specific slide. There are some frameworks available. For example, there are the latest, but you need to have the latest FPGA boards. I'm not sure whether the older ones will support Python-based thing, but the recent ones can take in Python frameworks like you may have heard of TensorFlow, a lot of these deep learning frameworks, and which could actually be you could write your algorithms on that, and that could convert into a netlist and be implemented on FPGA. So it is possible, but I think it's only the recent ones. I'm not sure about the old ones.
Okay. Then what is your opinion that VLSI is that is AI, artificial intelligence, going to take over the VLSI? Is it the what we are hearing is in true or what, or it takes some time, because all the research what is going on VLSI field, is currently it's going on neural networks. So for an example, the cadence which has been they started the TensorFlow, they have integrated into the software. So is that is feasible to carry over the research over that is based on that platform?
Are you asking whether the CAD tools of VLSI are going to use machine learning and deep learning?
Yeah, exactly.
That's already started. In fact, when I was in Qualcomm, before I joined Xilinx, I think we were already looking at a lot of these potential applications of deep learning.
So is that available for the research scholars, sir?
Yeah, there are a lot of papers being published. Some of them could be very
Okay.
proprietary to the company, but a lot of research is being published, and maybe I think I can try to, if that there is interest, maybe on the last day, if you can
Okay.
send some questions to
Okay.
organizers, I can try to put together some
Okay.
references for the audience, and then you can start reading through it.
Definitely, I will list out some of the questions and will put it to the. I will give it to the organizers.
Sure.
Yeah. Thank you.
Okay, I think that's mainly the last slide I had. So this talks about the potential applications of FPGAs and a lot of broad applications. I talked about the 5G, 6G infrastructure. For example, companies like Nokia and Qualcomm, and then Huawei in China, and a lot of other companies are investing heavily in 5G, and a lot of the 5G the network is actually the infrastructure is being built on FPGAs. Not on ASICs, because I think it's the FPGAs are sort of fairly the recent FPGAs are fairly competitive with ASICs, and they are using that. And then financial, this is another interesting thing. You must have heard about high-speed trading. A lot of high-speed trading, or pretty much all high-speed trading, is done with FPGAs. And then lot of medical devices or medical imaging and related acceleration is done through FPGAs. So it's a fairly significant and breadth of applications which people are exploring for the use of FPGAs as captured here. From an academic point of view, there are a lot of things which you could do, which could be coming in this area. For example, image and video processing, or simple things like for example, image for medical processing, the images for medical reasons. For example, you could build some simple accelerator or some sort of a core for taking, let's say, an X-ray or some other medical image. Try to look for it for any disease symptoms, right, like cancer or so on, and use your FPGA to sort of process that logic and run some computation, give some result out. A lot of people use that. And then industrial, it's heavily used for robots. And then I think I just go on and on, because there's so many applications, there's no end to it, and only the applications are becoming more and more. HOD sir, you have any questions? Does it answer your question or provide answers to your question?
Yes, sir.
Okay.
Sir, just because most of the faculty members, they are using a Xilinx. Hello, sir. I'm
Yeah, I
audible,
can
sir?
hear you. Yeah, I can hear you. Yes.
Hello.
Yeah, I can hear you. Am I audible?
Yes, sir. Yes, sir. You're audible.
Okay. I think he probably has some network issues, I'm guessing.
Hello,
So
sir.
we're nearly. Yeah, sir. Go ahead, please.
Sure.
Yeah, I
Yeah.
can hear you, sir.
Yes, sir. Yes, sir. Sir, because most of the faculty members, they have the Xilinx open source. What type of projects we can carry for either it may be a mini project or a major project? Either it may be a front end. I think we can do only a front end related projects with respect to a Xilinx. What type of projects we can carry for our students, sir, with respect to FPGA?
So not just front end, you can also do a lot of system design aspects also. Depending on what kind of board you have, you
Huh.
can build some fairly useful functionalities and features on your board. It can be
Because
like a
most of the colleges, some colleges faculty, they have their tool with respect to FPGA, and some of they have the CPLD.
okay.
So either it may be a CPLD or a FPGA kits. What type of whether we can carry a major papers through this FPGA or a CPLD tool, sir?
Yeah, I think if you have a board, then you can explore the what sort of functionalities are available on the board to try to build some simple system. We can start with something simple, not very complex, and build up the skills. Let the students use the tool and then the flows. Try to implement some simple logic, like for example, trying to build a simple state machine or a simple controller and things of that sort. For example, even you can try to build a very simple 8-bit or a 16-bit CPU using that.
Okay.
So
Whether it
that
is
kind of
possible to build any paper with respect to this, sir? Because most of the faculty members, they are looking for a paper publication. By keeping
I think
this CPLD or a FPGA kit, can we publish any paper with respect to either in the Scopus or at IEEE or elsewhere, anything?
it's possible, but I think I think you may have to we'll have to discuss that. I think we can plan it out. It depends on what level of complexity we want to address, what skills at that point those individuals have. Some of it may require them to know RTL and some of the digital design aspects. I assume some of them know that already. So if they know that already, it's a good starting point, which means we can build some simple to some complex, not very complex systems. But if you want to do some very complex or advanced systems, we may require more advanced boards, like for example, the Xilinx or the latest FPGA architectures. This could be slightly more expensive, but the point is that these boards allow you to do a lot of interesting AI ML kind of things, which are recently in the current uh, uh, sort of the last few years are the main focus of the design community, and a lot of papers are being published in this area. But it doesn't need to be only in ML and AI ML. It could be other areas also. And if that is the case, uh, there could be papers published in other areas where you could use simpler FPGA boards. So it all
Sir,
depends on, yeah.
sir, is it possible by using with respect to the VLSI tools, open source tools, whether faculty or a student can publish a papers either in the Scopus or a IEEE or any with respect to any top level journals? Please,
Uh,
please
I think
discuss this with any one of the sessions, sir. Because it is
so.
not possible for all the colleges, all the faculty members to get the Cadence or a Synopsys tool.
Okay.
By you, because open source tools means all the students or even faculty members will get the open source tools. By using this tool, is it possible to publish any papers?
Yes, sir. The open to if you're talking about open source ASIC tools, there are a lot of new open source ASIC tools. I can probably try to talk about that on the
Please,
last day.
please cover that in any one of the sessions, sir.
Yeah, I'll try to talk about that, and I'll try to maybe give a quick overview of what the flows are. And
Okay.
I think maybe the faculty can then explore based on the inputs I provide.
Okay. Okay. Sir. Thank you, sir. Thank you.
Okay, I think that's mainly it. So I just last two slides are nothing but these two deep learning accelerator built by Google. This is an ASIC, an application specific chip just built for better deep learning acceleration. For example, when you say hello Google, or for example, you are doing this when you start typing the search, a lot of predictive sort of search happens where even before you complete the whole sentence, Google is trying to predict what we're going to type and say. And when you're saying hello Google, is going to quickly anticipate what we're going to say or what you're going to look for as we are speaking, and try to sort of quickly get our queries. All of that is accelerated using Google's own custom TPU. It has this in its cloud form, and it's specifically meant to accelerate Google search and audio queries. And then this is an alternative for another AI/ML accelerator, and this is actually an FPGA based. Just to sort of show that the whole nomenclature is not separate anymore, that the same deep learning or AI/ML acceleration can be supported by an ASIC as done by Google and as done by Xilinx AMD, to have dedicated AI/ML engines along with the programmable fabric, which could again be used for machine learning or deep learning acceleration. Like, that's all I have, and I'll end my presentation here. If there are any questions, please feel free to ask.
Excuse me, sir.
Yeah.
Sir, quantum computing is coming up. Does it govern by the transistor logic, or what sort of states it has to realize a function?
Quantum computing is completely different. It's not based on transistors, not based on the way we use transistors. Transistors are based on the high-low or true-false states, right? It's based on binary. Whereas quantum computing is based on something called as entanglement. And that's completely different from what we currently use for compute. That's still, I think, easily 15 years away at a minimum, maybe even more. But a lot of research is happening on that. And I think that's an interesting area, but it requires a lot of specialized knowledge. So if you're looking to explore that, I think you may have to invest your energies and skills in a lot of areas like linear algebra, understanding some basics of quantum physics and quantum computation. IBM has this a lot of open material called, which I think they have kept a lot of these open material on quantum related aspects for the wider audience. It's called Qiskit, QISKIT. You can search for it, IBM Qiskit. If you want to learn about quantum, maybe this IBM's open material is would be like a good starting point if you're interested. Did that answer your question, Sanjay?
Thank you, sir. Yes, sir.
Okay. So are there any other questions? There were a few questions on the chat. Let's see if I can cover them. So which language is more preferred in the VLSI industry? Is it VHDL or Verilog? I think it's primarily, I shouldn't say primarily, but most companies use Verilog these days. And in fact, it's there's another variant of Verilog called System Verilog, which is used heavily. VHDL is used in very few companies. I think a lot of small companies may use your VHDL, and a lot of European companies use VHDL. But otherwise, I think Verilog is the one which is heavily used. And then RFICs are developed using the same design flow as ASICs. If not, RFICs, I assume you mean the ICs which are meant for wireless signal processing, I assume. If that is the case, they do contain blocks from the ASIC flow, but not everything. Some of them are built using a lot of custom design style, where we may use some specialized transistors and processing elements and other aspects on the chip. For example, if you have to build a lot of these high frequency or wireless chips require wireless signal processing support, which requires a lot of dedicated analog circuitries. For example, analog circuitry don't scale the same way as digital circuits. So a lot of specialized support has to be provided by the foundry. So if it's a complex wireless SoC, they may have a mix of regular ASIC flow and some custom or dedicated flow for the analog logic. So yes, you can build protocols on FPGAs. It's possible. Any other questions?
Sir.
Yeah.
Sir, it's audible, sir.
I can hear you. Yes.
Yeah, sir. You said exactly difference between the FPGA and ASIC, na, sir.
Yeah.
Sir, why they are preferring FPGA only? ASIC is an advanced one compared to FPGA, na, sir. With respect to cost, there will be ASIC will be the more one. Why they are using more FPGA only?
No one is using more FPGAs. It all depends on what you want. What I was trying to say is, previously, if you wanted high volume, let's say high volume, let's take an example, right? So you're using a smartphone and it's an Android phone. Android phone, let's say built by, let's say Samsung or any other company, right? So if it's an Android phone, then I think there's a huge volume of people, huge volume of customers, and significant customers you can serve using that Android phone, right? Could be as many as 50 million to 100 million. That's a big volume, significantly high volume, right? And in that case, Samsung could build its own chip using ASIC approach, or could get an ASIC from Qualcomm or MediaTek. So they do use ASIC in such cases, which is basically an ASIC SoC. But if it is, if you don't have such high volumes, but reasonably large volumes, let's say 50,000 to 100,000, even up to 1 million, but not more than that, ASICs are still not very power efficient, or cost efficient, because unless you have high volumes more than, let's say, 10 million, ASICs are still very expensive. So in such cases only people go for FPGA.
With respect to cost matter, you're saying that FPGA better compared to ASIC.
Not just cost. If you are looking for very high performance or very low power or very low area, ASICs are the best approach. But if you are not looking for very high performance, very low power, then people are okay with FPGAs.
Okay, sir. Thanks.
Okay, I think that's.
Excuse me, sir.
Yeah, go ahead.
Sir, basic difference between FinFET and MOSFET, sir.
Yeah, we'll talk about that in the coming days. I'll touch upon that when we talk about Moore's law and Dennard scaling and these concepts. We'll touch upon FinFET versus planar.
Moore's law still valid and cured.
Okay, sir. Thank you, sir.
Yeah, we'll cover Moore's law also on in that's it, same presentation.
Thank you, sir.
Excuse me, sir.
Yeah.
Sir, you talked about the power usage, no, sir? So FPGA uses
Correct.
more power than ASIC. So is there any chance that we could reduce the power usage by writing code in an efficient way, or somewhat in the code, if we could reduce the power, sir?
Yeah, that's a good idea actually, and that could be an interesting research. In fact, this is like a very useful research to do. For example, FPGAs, you could look at various power saving opportunities in FPGA and see whether your efficient code in an FPGA could reduce power compared to what, let's say, Xilinx's own software can do. For example, you can build a small controller or a state machine or even a small CPU, take it through the regular flow through the Xilinx FPGA software, Vivado, get some results out, dump the power, and then write your own code which has been optimized as you are planning. Then take it to the flow, implement the design, compare the power. If your approach for the same performance is giving lower power, then that could be like a good paper or a good sort of something which you can publish or try to present in a conference. That will be interesting to do.
Okay, sir, thank you.
Arun sir.
Yes, sir.
Yeah, already it is 9:30 almost. Please, can you carry tomorrow, sir?
Sure, sir. Thanks a lot. Appreciate all the attention. We will continue
Any
tomorrow.
participants, please ask any query if you have.
Yeah, I think we'll continue from tomorrow. Continue tomorrow, and
Yeah.
if you have any questions, we'll probably take in the first 10 to 15 minutes a few questions. Maybe if you can send it to the organizers, and they can share it with me, and then we'll try to cover a few questions, and then we'll start the session tomorrow.
Okay, sir. Okay.
Hello. Hello.
Yeah.
Participants, I request everyone. So before the end of the sessions, I think all the 6 days. Okay. So every participant has to minimum ask at least 3 questions. Okay. This is mandated as per the Atal guidelines. Okay. So already we have received those who are asked the questions. Okay. It is mandated for everyone to ask minimum 3 questions from your end before the end of the online sessions. Thank you.
Hello. Feedback and attendance form is sending through the WhatsApp. Sending through the chat box. Please, all the FDP participants are informed to submit the attendance forms. Only FTP participants are informed to submit. Others don't submit the attendance.
Sampath sir.
Sir. Sir.
So also inform the participants, it is mandated as per the guidelines. They have to ask a minimum 3 questions before the online session, before the end of the online session. Because I'm getting the query from the Atal FTP. They are saying that at least participants have to ask a minimum 3 questions before the end of the 6 days online FTP.
Okay,
This is mandate. Okay.
Okay, sir.
Because AICT is observing and they are whatever we are recorded, they are observing and they send the message that minimum 3 questions from the each participant it is required.
Okay, sir. That I will inform to all the participants.
Yeah. Thank
you.
And one more request, sir. Can you please share the feedback link in WhatsApp group also?
No, sir, because most of the participants are not joining the online session, sir. So it is compulsory to send the chat box, sir. Why? And because if you are send through the WhatsApp means without joining the session, they can submit the attendance, sir. So that we are sending through the chat box.
Because my battery is running out, so the draining out. So that's why I requested you.
Hello.
To share it.
Hello. As per the guidelines of the FDP, we cannot share the attendance in the WhatsApp group. Already we have created a WhatsApp group, but only we can share the feedback or attendance through the chat box only. This is the mandate. Because if we share through the group, without attending also some of the participants, they can submit the attendance details. That's why it is mandated from the AICT Atal FDP. We have to share the attendance only through the chat box. Those who are present, please submit your attendance status in the chat box itself. Thank you.
Thank you, Arun, sir. Thank you, all the participants. Tomorrow session we will start at 7 p.m. and the link will be shared at 6:45 p.m. Thank you. Thank you, Anandal.
Thank you.
Thank you, sir. And also thanks to Arun sir, Angit sir, and all the participants. Thank you.